PyramidFlow, high-resolution defect contrastive localization using Pyramid Normalizing Flow. During industrial processing, unforeseen defects may arise in products due to uncontrollable factors. Detecting and localizing these defects manually is time-consuming. To overcome this, machine vision offers automated solutions by detecting and localizing various defects. However, these defects are unpredictable, and high-resolution imaging and processing are required for accurate observation. Overcoming these challenges is crucial for practical automated visual anomaly detection in industry. In this paper, we propose PyramidFlow, the first fully normalizing flow specifically designed for anomaly localization. It develops the idea of templates from image space into latent space by normalizing flow, then performing contrast for anomaly localization. By combining the advantages of high resolution and high performance, we present a novel latent template-based defect contrastive localization paradigm. Our comprehensive studies show that it outperforms comparable algorithms that do not use external priors, even achieving state-of-the-art performance in complex scenarios. We then elaborate more on our implementation details. Our basic framework is based on normalizing flows, which bijectively map the image, X, to the latent space, Z, endowing the original space with a probability measure. The original probability distribution Px is estimated using log probability transformation, where the first term is based on the basic probability model defined in the latent space, and the second term is associated with subcomponents that determines the priors of the probability transformation. The basic framework utilizes normalizing flows to minimize the distance between normal samples, thereby forming prototypes, as known as templates in the latent space. In addition, anomalous samples are also encoded into the latent space. Then contrast with the template to locate the anomalies. Our framework is similar to contrastive learning, but lacks interclass items. So its loss function is only maximizing the intraclass likelihood. In this slide, we will explore the normalization of probability distributions. Typically, the loss function is optimized to maximize the image likelihood, which implicitly maximizes the determinant of the Jacobian matrix. However, this can lead to an uncontrolled compression of the score threshold, which may impact the performance. Through our observations, we have noticed that by imposing volume-preserving flows, where the Jacobian determinant is constrained to a constant value of 1, there is an implicit redistribution of the intra-image probabilities. This redistribution plays a key role in stabilizing the generalization performance. Therefore, we propose volume normalization, a novel method that operates on the coupling blocks to maintain a constant Jacobian determinant. During training, the pseudocode for this approach is presented in the table. Under volume normalization, the image distribution becomes equal to the latent distribution. In order to optimize the image distribution, it is necessary to assign a probability measure, using a known base distribution. In high-dimensional cases, the latent distribution can be effectively approximated by a standard Gaussian distribution. However, in low-dimensional cases, the latent variables are susceptible to zero-mean shifts. To address this issue, we propose zero-mean normalization as a way to normalize the latent variables. As illustrated in the diagram on the right, the normalization of the latent variables using templates significantly reduces patch variance. In this slide, we introduce multi-scale and high-resolution normalization flows. Inspired by the Laplacian pyramid, we propose the invertible pyramid, which decomposes the image embedding reversibly into components with different scales and frequencies, effectively decoupling high-frequency defects and low-frequency background. Additionally, the proposed pyramid coupling blocks explicitly map representations to the latent space, enabling the presence of receptive fields at various scales. In the following, we will present the training and evaluation process. The training dataset consists exclusively of normal images, while the test dataset includes both defective and non-defective images. During the training process, we randomly select two images and minimize their distance in the latent space. In the evaluation process, we encode the testing image into the latent space, then contrast it with latent template to localize defects. Below, we will present some experimental results. Firstly, we conducted a complexity analysis. In traditional neural networks, due to the non-invertibility of transformations, big O of L hidden nodes are required for backpropagation. However, in normalizing flows, all hidden nodes can be reversibly obtained, resulting in approximate constant memory complexity. Building upon this principle, we propose AutoFlow, a easy-to-use normalizing flow framework that greatly reduces the training memory usage. In addition, we conducted comprehensive ablation studies. Among them, volume normalization has the greatest impact. Further analysis shows that SVN with larger receptive fields achieves non-local localization by aggregating an extensive range of texture features, while CVN realizes accurate localization by shuffling channels. In a word, different volume normalization implicitly embodies distinct task-specific priors. We also noticed a significant performance decrease in those without latent templates. To summarize, methods 1 to 3 are critical for the proposed model, while tricks 4 help further improvements. Now, we introduce quantitative results on 12 registered classes in MVTech-AD. In our comparisons, the method based on pre-trained models, or using external datasets, is viewed as requiring external prior. In our implementation, we augment textural classes with flips and rotations, each with a probability of 0.5, while object categories do not undergo any augmentation operation. The detailed results are shown in the table. The fully normalized flow method is labeled as FNF, while the other abbreviations are denoted as ResNet 18, wide, ResNet 50-2. EfficientNet, B5 and Describable Textures dataset, respectively. The table demonstrates that our method outperforms comparable algorithms that do not use external priors, achieving the highest area under the per-region overlap score among all advanced methods. Furthermore, the visualization of the anomaly map clearly shows that our method achieves precise localization with reasonable scale. To fully illustrate our superiority, we experimented on the more challenging BTAD dataset, without any data augmentation. And other settings are the same as MVTech-AD. The quantitate results show that our method also achieves state-of-the-art performance, in both scores and visuality. Finally, in this figure, we present a summary of our work. In practical applications, machine vision systems serve as data sources, providing training and testing data. During this process, the training data is mapped to the latent template, while the testing data is mapped to the latent space, and contrasted with the template to generate anomaly maps. If defects are detected, human intervention is necessary to address them, either by removing or repairing the defective samples. Our proposed visual anomaly localization algorithm is engineering-oriented, significantly boosting the performance of machine vision detection systems and enhancing the accuracy and reliability of defect inspection efficiently. Thanks for watching.